Tokyo, one of the world's most ancient cities. It could become home to the greatest engineering marvel of modern man, the megacity pyramid. Over 3,000 feet high, it's a radical new approach to urban life. A three-dimensional city with skyscrapers suspended from it like fruit on a tree, and people speeding between them through a vast matrix of hollow supports. One of the greatest engineering challenges in history, it would utterly transform Tokyo Bay, the first offshore city ever built. But should it be built? Perilously perched on the Pacific Rim, it would be exposed to nature's wrath at its most devastating, the terrifying tidal waves called tsunamis. What would it take? Are their materials strong enough? Technology advanced enough? Energy abundant enough? Or would it jeopardize the lives of 750,000 people in a single gigantic structure? The Shimizu Megacity Pyramid, the future of urban living, or the next Atlantis? Drowned for eternity beneath the waves. A busy market in downtown Tokyo. Here, everything from today's catch to the world's hottest gadgets battles for shelf space. And no matter what the product, whether it's fish or chips, competition is fierce because space is tight all over Tokyo. With 12 million people squeezed between Mount Fuji and the Pacific, the whole city is packed to the rafters, in danger of collapsing under its own weight. With millions more flooding into the city each morning, something has to give. If a bold new engineering proposal becomes a reality, they may end up here, on the only vacant real estate around, right in the middle of Tokyo Bay, in this, a massive mind-bending structure called the Shimizu Megacity Pyramid. Its shape is familiar, but despite the echoes of an ancient architecture, this pyramid is unlike anything else on Earth. Because it's not a building. It's a revolutionary urban environment that squeezes 24 80-story skyscrapers and a population the size of San Francisco onto artificial land in Tokyo Bay. Its footprint would cover an area the size of 275 city blocks. To rent the equivalent amount of land in downtown Tokyo would run more than $10 billion a year. But the real marvels of this massive structure are these: the diamond-tough supports that will hold the whole thing up, the megatrusses. These are the bones in the circulatory system of the living city, and they contain the critical transportation systems that keep hundreds of thousands of people on the move, speeding through a glass and steel metropolis in the sky. A network linked by 86 miles of horizontal and diagonal aerial tunnels meeting at 55 transfer points called nodes they create a transit system as large as San Francisco's subway, but miraculously squeezed into an area just 1/50th the size. It's a complete, self-contained, self-sufficient city with everything anyone could ever need to lead a complete life from cradle to grave. If built, it would be the largest structure on Earth and the most extreme feat of engineering in the history of man. Is it too daring, too huge, too risky? Only time will tell. But something must be done to relieve the pressure on a city bursting at the seams.
The pyramid allows us to build a really, really big platform without destroying the natural world under it, to create a new city.
A glimpse of the future on the drawing board today? Will it be strong enough to stand up to the worst of nature's fury? The frequent earthquakes and tsunamis that plague coastal Japan. Could it be the greatest achievement in human history? Or merely a monument to man's vanity? If the past is any guide, it could turn out to be both. The Great Pyramid at Giza, perhaps the greatest human achievement of the ancient world. Perched on the edge of the Sahara Desert, it is the burial chamber of Khufu, pharaoh during Egypt's 4th dynasty. And though thousands of years removed in time, it still has valuable lessons to teach those who would copy its form. But the pyramid did not spring fully formed from the heads of its builders. It took centuries of trial and error to get it right. And yet, it's an engineering achievement that gives Japanese planners a solid foundation to build their pyramid. Because while it looks very different, the Shimizu Megacity Pyramid is proportionally similar to its ancient prototype. The complete structure is actually an assembly of 55 smaller pyramids, each about the size of the Great Pyramid in Egypt, but stacked 5 layers high over Tokyo Bay. But there is one crucial difference between the Megacity Pyramid and its ancient inspiration. The Japanese design is hollow, lacking the stability of a pyramid built of solid stone. And that raises troubling questions for Japanese engineers. Would their pyramid be safe from disaster? And can this 4,000-year-old design be updated for our world and built using modern methods and materials? Answers to some of these questions can only be found in a place far from troubled Tokyo. In the only spot in the world where someone would think to turn a mausoleum into a casino. Las Vegas, Nevada, land of fantasy. And home to an engineering first. A modern-day pyramid called the Luxor Hotel. This is what the Great Pyramid at Giza could have been if mummies had room service. Luxor's dimensions, an almost exact match for the Great Pyramid in Egypt. But the similarity is mainly cosmetic. Because even though Luxor looks as solid as the Great Pyramid, it's completely hollow. And inside is the largest atrium in the world, spacious enough to warehouse 9 747s. Or if this were the megacity pyramid, one of its towering skyscrapers. The Luxor Hotel is a massive structure.
The base of the pyramid is on 9 acres. There's 11 acres of glass on the exterior. And unlike the Great Pyramid in Egypt, that pyramid was made of stone. This is made of glass and concrete.
But it's not all fun and games in this clever replica. There's serious engineering here. And the building actually serves as a technical proving ground for the megacity pyramid. During construction, builders had to answer an important question, one that the Japanese must also confront. How to adapt construction techniques developed to build skyscrapers to erect a multi-story building that's not shaped like a box. Conventional box-shaped skyscrapers are more stable during construction because their columns stand straight up, less likely to topple. But there's nothing straight up about a pyramid. Its walls lean in at an extreme angle. Gravity wants to bring the whole thing crashing down at every turn. So during construction, builders had to erect Luxor's 4 leaning walls in tight lockstep with each other in order to keep all 4 sides in perfect balance. A first in high-rise construction. The megacity pyramid of Japan would require the same tightly coordinated construction scheme as Luxor, but on a vastly larger scale. Because engineers don't have just one pyramid to build in Tokyo Bay, they have 55 pyramids to construct, each the size of the Luxor Hotel in Las Vegas, interconnected and reaching 3,000 feet into the sky. Also, the megacity pyramid won't be enclosed like Luxor. Instead, it'll be totally open to the elements, because it would have to stand up to a powerful typhoon, where wind speeds can top 130 miles an hour. Designers considered enclosing the entire structure in glass to protect the people and buildings inside. But how would an enclosed pyramid stand up to nature's worst punishment? Luxor provides a critical clue. Before Luxor, no one had any idea how wind flows past a pyramid. So the hotel's designers asked wind engineers at Rowan, Williams, Davies, and Irwin in Canada to run some tests on this scale model. What they learned had a profound impact on the hotel's design. In a normal skyscraper, wind hitting the building breaks to the left and right. But Luxor's extreme sloping sides send the wind right up over the top, creating a dangerous turbulence on the opposite side of the building. Engineers discovered that within that unusual vortex, air pressure dropped drastically, possibly low enough to suck the heavy curtain of glass right off the building. Thanks to that timely discovery, engineers radically redesigned the windows to strongly attach them and thwart a potential disaster. Tests like these also confirmed for mega pyramid engineers that covering their structure in glass would be crazy, creating treacherous wind currents that could wreak havoc on the city below.
The wind impact created by the mega city project would be very unique, but because it's an open structure, it wouldn't have as much of an impact as it would if it was completely enclosed.
No change to the design was necessary. It would be safer to let the wind blow right through the megacity pyramid. But as every engineer knows, a design is worthless if it can't be built. It's a noble thing to dream big, but it's quite another to make those dreams a reality. Shimizu Corporation engineers quickly realized that daunting challenges stood in their way. They'd have to develop a radically new approach to construction, or their incredible vision would never stand a chance of jumping from the drawing board into Tokyo Bay. And of all the obstacles that stood in their way, one outranked them all. A problem so serious that it could surely kill the entire project. Calculations revealed that any attempt to stack the equivalent of 55 Luxor pyramids made of concrete, steel, and glass on top of each other was doomed to fail. The design was fatally flawed. The problem is here, in the 36 mammoth columns designed to hold it up. These massive columns, sunk deep into the earth, would be the largest underwater footings ever created. But even so, they would be hopelessly inadequate. They could never support the weight of an entire city of 750,000 people. Just one 80-story skyscraper made of steel, concrete, and glass weighs around 365,000 tons. The whole pyramid will weigh in at over 200 times that, trillions of pounds. Each of the 36 footings would have to support at least 50 million tons, 50 times the weight of the Golden Gate Bridge.
As we know, the pyramid could not be built today. Because of its sheer weight, it would collapse on its own.
Engineers knew they needed a breakthrough of unprecedented proportions, a material vastly lighter than steel and 1,000 times stronger. If such a miracle substance were even possible. Ironically, the answer turned out to be right on the tip of their pencils. Carbon. One of the most plentiful elements in the universe. Carbon doesn't look like much, but it is tough stuff. Squeezed into a crystal under the tremendous heat and pressure deep within the Earth, it forms diamonds. But most carbon comes in this form, graphite, and it's used to reinforce everything from golf clubs to fighter planes. To make graphite, a carbon atom locks arms with 3 neighbors to form flat sheets, 1 atom thick. Each sheet is incredibly strong and stable, although microscopically thin. It takes millions of these sheets just to form the tip of a sharpened pencil. Until recently, scientists thought graphite and diamond were the only 2 flavors that carbon comes in. But they've since discovered a 3rd microscopically tiny form of carbon, nanotubes.
A nanotube can be thought of as a piece of graphite that's seamlessly rolled up into a cylinder. Think of this chicken wire as this piece of graphite that I roll up into the perfect cylinder of a nanotube. It's extremely strong and resilient.
Even though they are far too small to be seen with the naked eye, carbon nanotubes are incredibly tough and very lightweight. When mixed with metal, plastic, or ceramic, tiny nanotubes could lend these materials their incredible strength, creating a new generation of super strong and super lightweight composites that could make steel obsolete. In fact, nanotubes are so strong that builders would need less material, reducing the weight of the pyramid as much as 100 times. And even better, nanotubes don't grow old. They last nearly forever. Built of carbon composites, Shimizu's pyramid could survive for thousands of years, possibly even outlasting Egypt's pyramids. Nanotube reinforced composites can also be easily shaped into nearly any form, like the cylindrical trusses of the pyramid. And they have one more miraculous property. Under the right conditions, carbon atoms form nanotubes on their own. It's what scientists call self-assembly. It's an engineer's dream.
We don't have to manufacture the structures under certain conditions. Those structures, like cylindrical nanotubes, will assemble on their own.
Anything that can build itself is sure to go over big in Japan, because in addition to being short on space, Japan is also short on skilled labor. Here at AIST Research Institute outside of Tokyo, scientists are planning to give construction workers a helping hand.
In terms of the humanoid robots, our research is aimed at having the robots at home, in the office, basically to coexist with humans and to work together.
Here, robots are learning to work in a variety of environments, from hazardous industrial sites to hospitals, even around the house. But it's on the construction site that they're really about to hit their stride. Some of these humanoid robots operate machinery, from forklifts to excavators, but they still need a human coach to call the plays from the sidelines. It's called telepresence, and the robots become the distant hands of a human operator. But they're not quite ready to fly solo. Their batteries drain too quickly. Their brains are stuck in their backpacks, and they're not very light on their feet. No match for this sporty fellow. Here in this restricted lab, until recently off limits to cameras, the next generation construction robot is learning the family business. He can go where no robot has ever gone before. A radical improvement, he's much smarter and more agile than any of his predecessors. The ability to walk on two legs is one of the things that separates man from beast. But no longer man from robot. Thanks to breakthroughs in programming and the very latest in gyros, joints, and balance sensors, this humanoid machine has taken its first steps towards true autonomy. And since, he's acquired skills at an amazing rate. Today, he's learning how to work with his human partner to move a pile of sheetrock. For now, the human is still the boss, and he directs the robot with voice commands. They begin with a little warm-up, a tradition on Japanese construction sites. Then, the robot uses its sophisticated vision to locate the edge of the board. Allowing it to reach out and lift it with its partner. Just as the human senses do, the robot senses tell it when its hands are supporting the full weight of the board, and its fingers close precisely around it. With a gentle nudge from the human partner to guide it, the robot walks across the lab and delivers its load in exactly the right spot. Is this the future of construction? The perfect employee? Hardworking, dependable, and cheap? Not quite yet.
今から50年後、100年後に
50 or
は
100 years from now, I believe that we can develop robots that will have a brain of an elementary or even high school student.
というものができると信じております。
These researchers believe that within a century or two, robots may take the place of human workers altogether, though they may not look the part. Robots can take any shape required. The intelligent machines that could someday build the pyramid's network of trusses might look very odd indeed. And what better design for a machine to spin a web of massive trusses than this? A spider-shaped robotic factory built to transform raw carbon and other materials into miles of supports, right on site. But not even an army of robots can solve the final construction problem. How to lift millions of pounds of trusses into the air and shape them into a pyramid 3,000 feet high. Nothing like it has ever before been attempted, and no existing construction equipment, no crane or jack could hoist these massive structures into position. But a visionary architect named Dante Bini has made a reputation doing the impossible, and Shimizu engineers asked for his help. They understood that they needed new construction systems.
So they asked me to conceive a technique, a technology which would allow the construction of this mega infrastructure.
Bini has spent his career designing buildings that can build themselves. He calls them self-assembling structures, and he first made a name for himself using his novel methods to crack one of architecture's trickiest problems: how to build a dome.
Dome is the most difficult structure to build and to design. So I like challenges, and so I decided to invent a system to build domes.
Domes and hollow pyramids have something in common. When complete, they're self-supporting and extremely stable. While under construction, however, they are extremely unstable. Traditionally, builders filled their domes with scaffolding to prevent the unfinished structures from caving in. That's how domes were built until the 1970s, when Bini set himself an impossible task: to build a dome of reinforced concrete in less than a day, using only air.
My idea was to try to use air to lift and shape the material.
This rare footage captures his attempt to construct a dome in Queensland, Australia. He insisted that a steady supply of air, even at low pressure, could lift and shape a heavy concrete dome. So with his small team, he set out to prove his system would work. On top of a circular concrete foundation, they began by laying out an inflatable membrane, essentially a balloon. The balloon weighs hundreds of pounds, but that's nothing compared to what follows. A ton of heavy steel reinforcement, held in position by an intricate network of high-tension springs. Then, like the icing on a layer cake, 300 tons of wet concrete. Followed by a second membrane to hold the cement in place. Finally, defying all logic, they began pumping air into the membrane under the concrete. Could this crazy scheme actually work? In less than an hour, Vinny's concept became a reality. The massive dome was up.
I was able to lift and shape to the final position 300 tons of wet concrete and steel with the pressure that you make puffing a cigarette.
In one day, Benny's system swept aside thousands of years of engineering practice. And he transformed domes, one of the most expensive and time-consuming structures to build, into one of the cheapest and quickest.
I'm able now to build a dome even at lower cost than a conventional structure in no time, because it takes about 60 minutes to lift and shape to the final position a dome of as big as the Pantheon in Rome.
To date, Benny has inflated more than 1,600 concrete domes around the world. Benny's success with domes led him to make a bold proposal for constructing the megacity pyramid.
My solution is a proposal to lift the shafts of these huge shafts of the components of the space frame using air pressure. This is an expandable telescopic truss. If you locate the trusses as indicated in this model, you can extend this by inflating balloon.
It seems impossible to use nothing but air to lift 4 huge trusses, each 1,000 feet long and weighing millions of pounds. But it will work, because physics doesn't lie. Now, if Pyramid City gets built, thanks to Benny and to intelligent robots, the construction process itself will be one of the wonders of the world. Because the pyramid will build itself. Robotic nanotube factories, agile as spiders, will spin a web of carbon trusses. while Binney's air-filled membranes lift the trusses into place, creating an intricate tubular geometry in which skyscrapers hang like pea pods. Freed from earthly constraints, these buildings can assume any shape that suits the fancy of builders, fine-tuned to best serve their final purpose as offices, homes, schools, or recreation spaces for 750,000 lucky city residents. But there's even more here than meets the eye. An inner, unseen beauty made possible by hidden technologies, making the pyramid, if not completely carefree, at least car-free. The first megacity to sever the oil umbilical. Like most large cities, Tokyo is choking to death on exhaust fumes. Almost 25% of the city landscape has been paved to form roads. But the Shimizu Pyramid won't have roads. Instead, people will travel everywhere inside these great hollow trusses. These diamond-topped supports are the circulatory system of the living city. How to build a rapid transit system inside these massive structures presents a novel problem to city designers. To move 750,000 people horizontally, vertically, even diagonally. Of course, building such a complex transit system won't be easy. There are so many different factors to consider. So here at the Obayashi Research Institute outside Tokyo, urban planners are experimenting with an eye-opening new way to experience ambitious new urban projects without breaking ground. These 3D glasses put test subjects into a virtual landscape, allowing them to move around in an imaginary world at will. In this case, it'll be Tokyo's newest transit system, a driverless electric train. With only a computer at the helm, the first leg of the planned system is already moving tens of thousands of commuters each day, in and out of Tokyo's newly redeveloped Bay Area. This stunning landscape of futuristic buildings would become the front door to the megacity pyramid. And this train would carry passengers from the old city to the new. Once inside, visitors would transfer to Pyramid City's own internal system, able to transport anyone anywhere in the huge structure far more swiftly than would be possible in a flat city. The secret is Pyramid City's three-dimensional structure. In a flat city, traveling across town can be a bumper-to-bumper nightmare. During rush hour in downtown Tokyo, traffic speeds average less than 3 miles an hour. It's literally faster to walk than to drive. But inside the mega pyramid, every destination will be a breeze to reach, thanks to autonomous personal transport pods like this one. It's called Ultra, short for Urban Light Transport, and engineers are working out the last kinks halfway around the world in Cardiff, Wales. If planners have their way, these driverless taxis will soon revolutionize mass transit, just in time for the densely packed Pyramid City. Each electric-powered car operates on its own, piloted by computer, and following a trail of magnetic crumbs scattered beneath the surface of the roadway. At transfer points within the pyramid, a traveler will step onto a waiting Ultrapod, enter the destination code, sit back and enjoy the ride. No driver's license required.
It really, in many ways, can be considered to be a horizontal elevator. this concept is the same here as going to pressing a button on a door, the door's open, and we now select horizontally anywhere in the city.
The result? Rapid transit that even the tortoise would love. No more stopping and starting. Steady as she goes wins the race. When all of Tokyo's transit systems are finally coordinated, residents will be able to step onto an ordinary subway and transfer to a driverless train that will shoot them into Megacity's base. Arriving at one of the spherical transfer nodes, it's a simple matter to change to the local system. Driverless pod or inclined elevator to travel to the very top, almost a mile in the sky. For the first time in human history, a vertical metropolis of 750,000 people and not a car in sight. But there's a problem with this utopian dream. It requires electric power on an unprecedented scale. Where will it come from? The solution may be at their feet, in the waters just off the bay. Anyone who doesn't believe that the world's oceans hold vast amounts of energy need only to look here to the rugged coast of Scotland. Or better yet, here at Scotland's wave jet, where the waves are a bit more manageable. Every 15-foot ocean wave that crashes onto a beach in the real world hits like a slow-motion explosion, releasing enough energy to power 5,000 homes. Capturing even a small percentage of that energy could solve many of the world's power problems. So these engineers are using their lab to learn how to turn waves into watts. The trick has been to develop a power generator that's rugged and efficient enough to wring maximum energy from the punishing environment of the ocean. Their current prototype does just that. Inside, a shock-resistant turbine spins on both the upstroke and the downstroke of the wave. But relying only on ocean currents for electricity leaves the power grid vulnerable to nature's most punishing disasters. Like a massive tidal wave that could destroy the city's wave generators in a single killing blow. But there are other ways to wring power out of water. With a little boost from the stuff that stars are made of. Hydrogen is a super light gas that packs a heavyweight punch. Burned as fuel, it powers the space shuttle into orbit. And in hydrogen fuel cells, it's used to generate electricity, keeping the shuttle up and running, making it possible to live in space. Fuel cells cash in on one of the simplest chemical reactions in nature. 2 hydrogen molecules combine with 1 oxygen molecule to produce H2O, water pure enough to drink. Plus, a tiny squirt of electricity as a bonus. No moving parts and no pollution. But there's a price for everything in this universe. So, of course, there's a catch. Unfortunately, most of the hydrogen on Earth is already spoken for. Happily married to oxygen in water. But not if Maria Girardi has her way. She's doing her best to break up the happy couple, with a little help from algae. Pond scum to its friends.
Algae are aquatic microorganisms that are normally known as pond scum, and they can use sunlight as a source of energy to run their metabolism.
As anyone with a nose knows, algae-infested ponds stink. But what may be revolting to some smells like eureka to scientists like Girardi, because that gas is full of valuable hydrogen, liberated from the water by algae. In fact, all these gassy little guys need to produce the hydrogen that can power a fuel cell is a quiet place in the sun and enough room to spread out.
I think the idea of a pyramid in the middle of a water, in the middle of Tokyo Bay, could be supplied of energy by algae growing on floating containers and using sunlight to produce hydrogen.
Imagine the most technologically sophisticated city in the history of man, powered by pond scum, plus the pounding power of waves, and even the winds that constantly rake the globe. The megacity pyramid will never be a burden on Tokyo. In fact, it will be a boon, producing a superabundance of clean energy and taking the strain off the crowded city, reducing pollution, and improving life for everyone. Yet worries linger. Can the pyramid's builders really entrust the lives of 750,000 people to a structure this enormous and in truth this vulnerable? Especially here, smack in the middle of one of the most naturally violent places on Earth. Japan rests on the western edge of what geologists call the Ring of Fire. These are the explosive fault lines that ring the Pacific. Friction points where the continental plates grind against each other and release their pent-up energy in massive volcanic eruptions. And worse. It could happen anytime. The year is 2110, and the newly completed pyramid has become the proud centerpiece of a future Tokyo. But hundreds of miles away, a magnitude 8 earthquake rocks the floor of the Pacific. In Tokyo, the earthquake would shake the city. Most modern skyscrapers and other buildings rely on isolation technology that can protect them. But the worst is yet to come. Triggered by the quake, a massive tidal wave, a tsunami, is already racing towards Japan. This supercomputer simulation shows how a tsunami up to 1,000 miles wide, traveling up to 600 miles an hour, could crash from one end of the globe to the other, sowing devastating destruction everywhere it lands. The last tsunami to do real damage on a Japanese island hit in 1993. A 100-foot-high wall of water destroyed 400 homes, killed 200 people, and ruptured gas mains, causing a devastating blaze. In the blink of an eye, nature reduced this coastal community to rubble. And this tsunami is even larger, a beast of another magnitude. It would hit the pyramid with the force of a nuclear blast. Word goes out to evacuate. But there's no time. 750,000 people stranded in the path of certain devastation. Their survival would depend on the building itself.
The pyramid is a really, really big structure. So at the bottom, if there's a tsunami, if there's a fire, It's a problem for the people at the bottom, but it won't reach higher.
The monster wave roars into the shallow bay and grows, reaching 150 feet. And then it comes crashing in, delivering its killing blow to the Pyramid City. The giant trusses groan under the stress, but they hold. Thanks to its super strong carbon supports, the pyramid withstands the worst that a raging sea can throw at it. Not only that, the building's enormous size actually protects the city behind it, possibly saving thousands of lives. The Shimizu Megacity Pyramid. Will this incredible dream ever become a reality? For its designers, the very question may be beside the point.
ピラミッドはいろいろ話してきましたけれども、
The pyramid is not something that we're going to build right away. So in that sense, it's a dream. But by pushing this dream, we're pushing the progress of technology as well.
A modern marvel in an ancient form. Whatever its destiny, the fate of civilization may depend on dreams like this. The latest chapter in man's quest to etch his mark on eternity.